The real frontier underwater is not speed, it is trust. Trust that a powered diver can do precise work and still come home safely with a clean, auditable record of what happened. As of 2026, personal underwater mobility is still mostly simple. Fins, buoyancy gear, exposure suits, breathing systems, and sometimes a diver propulsion vehicle. The biggest gains usually come from reducing exertion during transit, not from a fully integrated, semi-autonomous exo-suit that manages the whole dive. That gap matters because water punishes every mistake. Drag rises fast, visibility collapses, communications get thin, thermal loss steadily eats attention. Add pressure, entanglement hazards, and fatigue, and more power can easily mean more risk. So what would make an integrated dive exo-system truly valuable? Start with the metric that actually counts: task radius. That is the distance and duration you can work while preserving safe return margin. It includes breathing reserve, heat reserve, navigation confidence, and cognitive capacity. People get pitched top speed or battery capacity. A better question is, how much safe work per hour does the system produce, and how reliably? A second insight is that the technical substrate already exists, just not in diver gear. Underwater robots have benefited for decades from serious hydrodynamic modeling. A verified 6-degree of freedom model for an autonomous underwater vehicle can estimate thrust, drag, trim, and control response in real conditions. Translate that thinking to human-worn systems, and you can define a control envelope. You can ask which postures, currents, and loadouts stay stable and which ones turn unsafe. But models are not the hard part. The hard part is human-safe shared control. Most diver propulsion vehicles today are direct manual control. Unmanned vehicles have more mature station keeping, return to origin behaviors, and basic avoidance. For a diver, autonomy cannot behave like a drone. A diver can panic, get disoriented, or fixate on a task while the situation degrades. Shared control has to blend diver intent with automatic stabilization without trapping the person, over-accelerating them, or making orientation worse. Fail-safe behavior has to be boring and predictable. That brings us to navigation, the quiet constraint that shapes everything underwater. GPS feels simple only because a huge precision infrastructure does the hard work for you. Underwater, you lose that entire stack. Acoustic positioning has latency and coverage limits. Optical links need line of sight and clear water. Inertial systems drift. Magnetic cues can get noisy near infrastructure. So a serious exo-system needs a positioning integrity layer, not just a position estimate. It must know the difference between known position, bounded uncertainty, and lost navigation confidence, and it must change behavior accordingly. Once you accept that, the next frontier becomes coordination. Underwater work sites are increasingly mixed environments. Divers, scooters, autonomous vehicles, remotely operated vehicles, and fixed beacons all share the same space. Networked subsea sensing has existed for a long time. The lesson is orchestration. In a modern work site, coordination needs local traffic rules, low bandwidth intense signaling, and mission logs that can be audited later. Without that, you get ambiguous authority, acoustic interference, and near collisions that nobody can reconstruct. Environmental constraints are also moving from nice to have to procurement reality. Microplastics research has documented how particles move, aggregate, and carry contaminants. That matters for suits, coatings, seals, and polymer housings that abrade over time. If powered mobility scales up, shedding is not just a quality issue, it becomes a governance issue. Low shedding materials, abrasion tests, battery recovery, and end-of-life retrieval stop being optional, especially in protected zones. Maintenance is the unglamorous limiter that decides whether these systems are deployable. Saltwater corrosion, biofouling, pressure cycling, and repeated decontamination can destroy reliability. The strategic takeaway is simple. Surface treatment, sealing, and cleanability are first-class design variables, as important as thrust. Now zoom out to what is proven, what is plausible, and what remains speculative. It is proven that propulsion assist can extend range and reduce exertion. It is proven that 6 degrees of freedom dynamics can be modeled and validated for underwater vehicles. It is proven that distributed subsea assets can coordinate as networks. What is plausible, but not yet a certified category, is an integrated exo-system that combines propulsion, trim assistance, navigation aids, physiological monitoring, and mission logs. Shared control station keeping is plausible in bounded work sites for trained users if thrust authority and fail-safe modes are tightly constrained. What remains speculative is a fully autonomous, human-worn exosuit that can navigate complex spaces and execute rescue-grade decisions without diver skill. For strategy and capital allocation leaders, the decision lever is straightforward. Procure around task metrics, not speed claims.